Okay, everybody, we're going to get started. So I want to welcome you to the ASHRAE New York Designer Series, April 28th, 2022. The topic today is applications of radiant heating and cooling systems in buildings. And this is presented by former ASHRAE Society President Bjarne Olesen of the Technical University of Denmark. So we're very happy to have him with us today. My name is Ben Rodney. I'm the president of ASHRAE New York and appreciate you all being here today. I wanted to just talk about a few events that we have coming up. So on May 5th, for those of you interested, we have a tour of Belimo's factory in Connecticut. We actually have a bus leaving from Grand Central. So if you're interested in that, you can sign up on our website, www.ashraeny.org. And that does have PDH credit and lunch. We also have a tour of Central Park coming up for any YEA members. So if you have any young engineers that you know that would like, or anyone that would like to join us for a tour through Central Park, please sign up and look forward to seeing you there. And then our May dinner meeting is all about acoustics and HVAC design. So we have a distinguished lecturer, Mark Fly, who's a director of the NAIC laboratory for AON, also an ASHRAE fellow. And that will be our past president's night. So that should be a great dinner meeting to finish our ASHRAE year. And then we also have our annual gala coming up on May 20th, which is a casino night at Gotham Hall. So tickets are still available. So if you're interested, please sign up for that on our website. I wanted to introduce our speaker, Bjarne Olesen, who's a professor at the Technical University of Denmark. He is an ASHRAE distinguished lecturer, an ASHRAE past president from 2017-2018, holds a master's degree in civil engineering and a PhD from the Technical University of Denmark. He's published more than 450 papers in over 90 peer-reviewed journals, as well as all the other accolades that you see here. So quite an impressive career, and we are very thankful to have him here today. If you have any questions, just type them in the question chat. I'll bring them up as we go along. At the end, there'll be a survey that pops up. If you fill that out, we will then get you your PDH credit and send you your certificate. And then we will make this recording available on our YouTube channel. So make sure to subscribe. And you can contact us at ashraenyc@gmail.com. So that is it. And I will hand it over to Bjarne.
Okay, thank you. So good afternoon, everyone. Sorry I couldn't be in New York, but I'm glad to be able to present the application of radiant heating and cooling systems, which I have worked with since my PhD, which were in fact on what are acceptable temperatures on floor heating and cooling systems. What I'm going to talk about is not new. It has a history of a couple of thousand years back, going back to China and Korea, where they were using the floor or the flue gas from the cooking pot circulate under the floor and then up between two walls like a chimney. So in this way, they were heating the floors. So you could say in this way, it was not hydronic, it was warm air under the floor. Similar when it came to Europe more than 2,000 years ago, the Romans, they were using them in their Roman baths. But again here, it was warm air circulating under the floor to heat up the floor. Nowadays, it's all hydronic. So what is radiant heating and cooling? Well, we also often call it low temperature heating, high temperature cooling, because you are using large surfaces for the heat exchange, like the whole floor, the ceiling, or the walls. So you can have a relative low over temperature for heating, and the cooling temperature for cooling will be relatively high, close to the room temperatures. So we are talking about system where many hydronic system where the water temperatures are in the range 77 to 104 degrees Fahrenheit for heating. In cooling, we are talking about in the area 61 to 74 degrees Fahrenheit. You may, some of the other slides, you may have some problems with the unit. Not all of them are in your unit, but I hope you will still get a feeling for where we are regarding temperatures and heat output. For cooling, of course, there's some limitation due to the dew point. You have to take into account, so that may limit the cooling possibilities. There's a wide range of systems which we call radiant heating and cooling, both for residential and non-residential. So I'm going to show some of the boundary conditions, design conditions, what heat exchange coefficient can you use. But I'm also going to show several examples of buildings with a radiant heating and cooling system. So one of the advantages is that if you are not using such a high temperature for your heating, you can combine it with low energy sources. Heat pumps, you will increase the efficiency of the COP because you don't have to heat up to such a high temperature. Ground coupling is often an important way of increasing your performance. You may use waste heat or solar energy. And for the cooling, ground coupling, you may bypass, in fact, the heat pump to get enough cooling. I'll show examples of that. So you can really increase the efficiency of your energy sources by large surface radiant systems. The concept of the systems are that we normally say you must have about more than 50% of the heat exchange is by radiation, and then the rest by convection. With a warm air system, more or less 100% is by convection. You can have heating and cooling panels that is often from ceilings, suspended from the ceiling, so which you install more or less when the building is finished, like you had radiators and so. You may also have systems where the piping are embedded in the surface of the building. And then some systems which are becoming more and more interesting is where the piping are embedded in the structure of the building. So you're using the thermal mass of the building. And this can be important in the future where we want to have zero carbon emission building and we want to use the energy when renewable energy is available. So that's why you may have some advantage by having a kind of storage in the building itself. The suspended cooled ceilings is panels like you can see here. It's often metal panels, and then you have on the back side, down in the right corner, you may have tubing, which could be copper tubes, but you can also have a plastic tubing which circulate cool or warm water. Often you use it like 100% coverage of this ceiling. Of course, the more area you cover, the better performance you get. But it could also be like islands, small islands suspended over the workplaces. There's also systems where you have very thin piping integrated in gypsum board, so easily to mount. or even what we call capillary tubes, also very thin tubes, which are mainly put into the plaster on the ceiling. So in this, you have a very kind of low mass system. I just want to show that one building here from Tokyo, which won ASHRAE award for design award for low energy or innovative buildings. It's in Tokyo. It has radiant suspended radiant panels, but combined with chill beams at the perimeter. Because sometimes for cooling, you are limited by the dew point, and in the perimeter, it could be that you want to have some extra power. And chill beams goes very well with the radiant panel because they use basically the same water temperatures, so they go very well together. Here you see the building where you have the radiant suspended radiant panels, and the air system is supply at the ceiling but return at the floor to get a good mixing in the space. So that's just one example of a system of a building which has been presented also in the ASHRAE journal. Let's look a little on the radiant surface heating and cooling system. That's where the piping are embedded in the floor, wall, or ceiling. But the part where they are embedded is insulated from the main structure. So you have some thermal mass, but not that that much. They are very common. Floor heating is in Middle Europe, Scandinavia, more than 50% of new buildings will have floor heating, if not 80%. And I'll show you also that a floor heating system can also be used for cooling. The system I will talk a little more about also is where we are trying to use the thermal mass of the building. So you integrate pipes in the main structure, here in the slabs in a multi-story building. Typically, it may look like you have the pipe between the upper and lower reinforcement in a concrete slab. And most of the heat exchange is over the ceiling, because often you may have a raised floor for IT installation and so on. So how can we determine the heating and cooling capacity? What do we know about the heat transfer between the systems and the space? We know from experiment, but also from theory, pretty well what the heat exchange coefficients are. So if we now take a floor system, because they are different, if it's a floor system or ceiling system or wall system. So you have to be very careful when you calculate the heat exchange. So for a floor system, for heating, you can at the design stage get up to 11 watts per square meter per year. So it's about 1.9 BTUs per hour per square feet per degree Fahrenheit. That's for the floor heating. But for floor cooling, you have a much lower heat exchange. The reason is that for heating, warm air rises, so you have a high convective part also. Still more than 50% is radiation. But the heat exchange by radiation is from the same for all systems, about 5.5 watts per square meter per degree, which is about 1 BTU hour per square feet per degree Fahrenheit. So this radiant part is the same, but it's the convective part which changes. So for floor cooling, where you cool the air close to the floor, you will not have the air rising in the same way. So your heat exchange coefficient is much lower, down to 7 or 1.2. So 80% of the heat exchange is here by radiation, and the small part is convection. For ceiling, it's the other way around. For a cold ceiling, cool air falls down. It's heavier than room air. So you have, again, here a significant part with convection. So you get about the same heat exchange coefficient as the floor heating system. So you can say a floor system is most efficient for heating, ceiling system is most efficient for cooling. But for both of them, you can do cooling with a ceiling, and you can do heating with the ceiling, and you can do cooling with the floor. If you're using the wall, it's not so common, but in some museums and other, they are using the pipes integrated in the walls for heating and cooling. Here, the heat exchange coefficient is the same, 8 if you are heating or cooling. So that's the heat exchange coefficient. But now the question is also, what is acceptable temperatures on the surfaces? How low temperatures can you go to, or high temperature? And here the comfort comes into play. So when we did studies on acceptable floor surface temperatures, we could see that for cooling, you could go down to 19-20 degrees centigrade, which is about 66-68 degrees Fahrenheit. But for sedentary, I recommend not to go below 68 degrees Fahrenheit on the floor. For floor heating, you could go up to about 29 degrees centigrade, about 84 degrees Fahrenheit for the design. But that means major part of the year, your surface temperature of the floor would be much lower, but that's for the design value. It is allowed to many standards in the perimeter, which are kind of outside the occupied zone. So let's say the first meter along a window, you could go, especially for heating, with a higher floor temperature to get some extra heating to compensate maybe for some cold downdraft from a window in winter. For ceiling, the radiant asymmetry for heating is a limiting factor. So it depends on the construction and the windows, but you can go up to ceiling temperature to 27 to 30 degrees, so 80 to 86 degrees Fahrenheit. Higher, you will have, the people will feel too warm head on too cold feet, so they don't appreciate that. So this radiant asymmetry will set the limit for how much you can heat. For cooling, people are not so sensitive if they have a cool head and warm feet. So here, there's really no limitation because of radiant asymmetry from a cool ceiling. But the limitation is more in the dew point. Do you have dehumidification? Don't you? So you have to follow the dew point. Normally, I say you shouldn't go lower than 17 degrees, which is about 62, 63 degrees Fahrenheit on the surface. So when we now look at the requirement, the comfort requirements, the limitations due to dew point and the heat exchange coefficient, what are then the maximum heating cooling capacity we can obtain from the system? And for floor heating, it will be about 100 watts per square meter, about 31 and a half BTU per square feet per hour. For cooling, it will be less than half. It will be about 42 watts per square meter, or about 12.7 BTUs per square feet per hour. For the ceiling, it's the same, but now the high capacity for cooling and a lower capacity around 42 watts per square meter for heating. And the parameter you could then get, if you have a higher surface temperature on the floor and the parameter, of course, you will then get also a higher heat output. So these are some of the design limitations. I will, however, come back to the floor cooling because there are some additional advantages with the floor cooling. So how to find out with pipe distance and what water temperature is needed? There is international standards. There's also a handbook, and the manufacturers they have calculation method or diagram where you can find out depending on what water temperature you want to have on the surface of your system, what surface temperature you want, what you need for water temperature. This all depends on if the pipe distance is smaller, you can have a water temperature closer to room temperature. It also depends for floor system on the resistance above between the pipes and the space. But these are all something that your manufacturers can help you with. What often is used to show the performance and calculate the heat output is finite element or finite difference method. These calculation programs are easily commercially available. They're not so expensive anymore. You specify the pipe distance, and you only have to look, if here a floor system, you only have to look at a small part of it because you assume isothermic conditions between the pipes. So you look at what is your heat conductivity of your floor covering. Is it the carpet? Is it tiles? What is the thickness? The same where the pipes are embedded. What insulation do you have below the pipes? And to limit the heat transfer to the structure of the building. And all this you put in the calculation, and then you can get values on top here for the, here we are doing a cooling. So the question is, what surface temperature you will get here? You will be around this calculation about 22 degrees on the surface temperature, and you will have a heat put about cooling about 27 watts per square meter, which is about 9 BTUs per square feet per hour. So this calculation method is very valuable when you design your system. What is a little more complicated, so for most of those where you have pipe embedded in the surface, you can use these static calculations of the heat output and to see if they meet your cooling load or heating load. For what we call thermoactive building systems, where you now have pipe integrated in the main mass of the building, it's a little more difficult because this is a very dynamic system. You have a lot of thermal mass, and here we are often using a building simulation. Most building simulation programs, they will have the capability of simulating a thermoactive building system where you have pipes integrated in the building parts, both in walls or ceiling or floor. So Energy Plus or Transit, they can all do a calculation of the heat output. The trick by using this thermal mass, let's say in an office in summertime, that is when you have a full air system. Here you have 24 hours. Here you have the occupied time from 8 o'clock in the morning to 6 o'clock in the afternoon. And here you have the loads. People are coming in the morning, it increases, then it's a west-facing room. The sun will come in and will increase the load. So when you have an air system, you have to design it for the peak load up here. Now, if we are using the thermal mass system, we are basically absorbing heat during the day and cooling down during nighttime. So we may not run the water during daytime, but we have an air system because we need ventilation. and we are using that to remove some of the heat during daytime. So what is removed during daytime is partly this heat from the ventilation system, and then we are storing energy or heat in the slab. Then when people have left, we cut down for the ventilation, and now we start cooling on the piping system in the slab. So the area under the blue curve, which are what we are removing during nighttime from the slab, and combined with the area under the green curve, what we are removing during day, should be higher than the total energy put into the building. But you see now your peak load is smaller than if you had 100% air system. So you can design your system for a lower peak load, which is an advantage. The other thing is that a lot of the energy you are using is during nighttime, where often the electricity to run the pump and so is cheaper. So basically, we try to design it so you can use the nighttime condition also for your system. So how do we control a radiant heating and cooling system? Well, this is an example if you had a floor system, but it's basically the same. If you have both heating and cooling, so you may have a chiller, you may have a boiler, and you want to control the supply temperature. Now it's a residential building to the building. So you control the same temperature to all the rooms. But each room, they have a room sensor and are connected to a valve to the pipe circuit for the room. So if it's warm enough or cool enough, you just shut down for the valve so you don't have circulating of water in this room, while you may still circulate in the other rooms. So that's typically how it's made, that you have the same water temperature to a whole residential house or a section of a bigger office building, and the individual room is then controlled by a room thermostat that shut off or open a valve. For controlling the supply water temperature, you are mixing, if you are heating from the boiler and the return. And then you have an outside temperature sensor. So it's very cold outside, you supply a higher temperature. But if you get warmer outside, you decrease your temperature. If you also have cooling, you now switch over to the chiller. And for cooling, it's always recommended also to have a humidity sensor, because in this way you know the dew point in the space and can limit the supply temperature so it doesn't get lower than the dew point. And that means all other temperatures in the system will be higher than the dew point, and you avoid any condensation on the surface or in the structure. So that's one way of controlling. I talked about we have some mass, for example, in the floor system, but especially also in the tap system. So on one hand, you can think it's a very slow system. Yes, it's slow when you want to change the temperature level in the space. But if you want to compensate for changes in the internal loads, then the over temperature, here we have a well-insulated building, the over temperature of the floor is only 2 degrees centigrade of the room temperature. So a small increase in room temperature will automatically decrease the heat output. So there's this self-control, which makes it pretty fast because you have temperature on the surface very close to room temperature. So on the one hand, you could say it's a slow system, but on the other hand, to compensate for changes in internal load, it's not that slow. So let me show some examples. As I mentioned, for the activated thermal slab, we want to have the slab absorb the energy during daytime and then cool down during nighttime. So often here we do a building simulation And here are different scenarios how to control the water supply temperature. Here on the axis, you have the operative temperature in the space. I simulated here in office space. And the most you can cool is by running the water at the dew point. And you see here the green is where you are in the optimal comfort range, 20 to 22 degrees. No, 20 to 25 degrees. We're talking about cooling in summer. But you see you're using pretty much energy for the pump also. I will come to the total energy on the next slide. But if we instead are controlling the supply water temperature here for cooling according to outside temperature, I'm only looking at summertime, May to September. We see we can run the pump much lower. Here in this case, we run the pump much shorter time than if we had the maximum cooling. And again, you see more than 90%, we are still in the green. We get 5–10% where the temperatures get about 25. But again, we are in a reasonable comfort zone also here with a much more efficient control. If we now look on the energy, when we try to run it at the maximum cooling at the dew point, we have some time to reheat because it's getting too cold. Remember, we have this heavy mass. We should take care not to cool too much. So this is what's happening if we are running at too low temperatures. So we reheat, and that's not a good energy economy. Whereas if we are controlling the supply water temperature according to outside temperature, we see here we avoid very little reheating. We have a much lower energy use here, the energy use in kilowatt hours. Also the energy use for the pump is much lower. So some control according to outside temperature is recommended also for the high mass system. I'll get now to show some examples and also how you do installation, because one of the tricky things with the thermal mass system is that you now have to get into the building when the building is constructed. You cannot wait until you have the main structure of the building and then put in your insulation and your floor tubing and the screed on top of the floor tubing. Here you come with the tubing, the pipes, when the building is being constructed. So often here, what we did with the first system when we started with this type of system in the late 90s was it came to the building site as like a 15–20 square meter pre-installed piping on a metal mesh. So you can put down very quickly the piping on the lower reinforcement. And then the upper reinforcement was put in, and the pipe was then hanging between the two reinforcements. In this, there's no problem with the safety or with the structure if you have piping between upper and lower reinforcement. And then you pour the concrete. When you pour the concrete, before you start pouring concrete, here is an example. You have the piping, but it's difficult to see because you have the metal from the you have in the concrete for the reinforcement. But you do a pressure test. That's shown here. You do a pressure test to make sure that nothing had happened with the pipe during installation. And normally nothing will happen. They are pretty strong, the pipes, so it's surprisingly few cases you have. But then you pour the concrete and take a pressure test again. And if you have done that, then the pipes are really safe and protected, and nothing can really happen with the piping. There are also manufacturers now who install piping in the prefabrication of concrete slab. This we have some in Denmark, but especially in Netherlands, it's very often you use prefabricated slabs. I just want to come back to the floor cooling, because I said not many people think about it, that if you have a floor heating, you can also use it for cooling. And especially where it's an advantage is where you have some direct sunshine on the floor in atriums, but also in residential if you have large windows, because if you have a cool floor, it will directly absorb the energy from the sun radiation. And in this case, you can go up to cooling capacities of 100 watt per square meter or 32 BTUs per square feet per hour. So this is a very efficient system in building where you have large windows with direct or indirect radiant exposure of the floor, especially from the sun. So, for example, here are some example. We have our opera house in Copenhagen has a large window facade here, and we have in here both floor heating but also floor cooling. A big shopping center here in Spain, another museum using the floor again because they have a lot of sun radiation through the glass. I'll just present you now the largest structure which we're using floor cooling, and that's an airport in Bangkok, which was constructed beginning of 2000. And here it was decided to have a floor cooling. Here you see in one of the concourses on the installation here, piping all over. You could say the architectural design may not be the most intelligent in Bangkok, which has a lot of sun load, very high humidity, very warm weather. And you look here at the envelope of the concourses, you have a lot of windows. So you will get sunshine into the concourses. Except in the main terminal, there are some shading here, but the others are exposed directly sunshine through these glass parts of the envelope. So the idea was here to have a floor cooling with a floor temperature around 21 degrees, 13 degrees supply water temperature, 19 degree return water temperature. And it would be put in the floor in the concourses, but also people in the moving and some of the other stores above the lower lower part of the concourses. It was done a couple of things also with the roofing. They were put in some low E coating that reflected some of the radiation. So you could say that the cool floor mirrored itself in the ceiling. There was also put it in some fritted glass, so you had some solar reflection. So some of the incoming solar were reflected to lower the internal loads. There was done.
We have a question.
Yes.
In a project like that, how are you thinking about zoning for the radiant cooling, and what would be considered too large a zone for the piping or too small a zone? How do you think about that?
Yeah, what you think about is, of course, a pressure drop. If the zoning is too big, you use too much energy on your circulation pump. Here, the zoning were about 100 meters of pipe, and the pipe was about a 20 millimeter pipe. So it depends on the size of your pipe, what the pressure drop will be. But often it's about 100 meter in that range.
And then another question kind of playing off of that. So if you do the pressure testing to make sure that there's been no rupture of the piping, is there any redundancy built in or any additional piping installed in case there was an issue? Or if there was an issue with the piping, how would you resolve that once the slabs were poured?
Well, it depends on how it occurs. When I was in industry working with this, we had one case where people had, they were constructing during winter time. The building was not closed yet, but they tested for leakages with water during winter, but forgot to take out the water again in the pipe, so they froze, and they had then a lot of leakage. In this case, you can basically not use the pipes again, but that was a mistake from the installer. So normally, if you know where it is, we have also seen that in an installation, then later on the architect finds out, oh, we need to drill some holes here. I need to have some ventilation ducts going through, and they forget about that they have a floor piping. Then of course you know where you hit the pipe, and in that case you can make a little bigger hole around it, and then you have connectors where you can connect the pipes, and they are as secure as the pipe itself. So that is possible to do it. If you don't know where the leak is, then sometimes you circulate warm water and use an infrared camera, and you can see where the leak will be. But very often, what I remember is it didn't happen so often, and when it did, it was because somebody was trying to bore a hole through a pipe, and then you know where it is, and then it's not such a big problem to repair it.
Great, thank you.
So this is just showing a CFD analysis, how using this type where it will be cool down here where the people moves, but up here under the ceiling, it may still be warm. By this, they did, by calculation, a comparison by a full air system with this one combined with air and the hydronic. And they calculated they would save about 30% of the energy because of higher efficiency of the ventilation system, and it's cheaper to move energy with water than with air. Here you see the installations done, and here what they had for ventilation was a displacement. At the right hand side, left hand side, you see big diffusers. So here air is coming out at a little lower temperature than the room and slowly pressing out the old air. So it's a combination of a floor cooling with a displacement air system. One question here was also about condensation. Did we have to the supply pipes, which are only like 13 degrees, would we risk any condensation? Did we have to insulate these pipes? Well, what we did was we put the manifolds inside the air distributors, because the air was coming in with an air temperature of 16 degrees and 10-degree dew point. But the supply water temperature didn't go below 13 degrees centigrade, so always above the 10-degree dew point. So we didn't have to insulate a supply type around the manifolds. So that was one example. I think I will just skip this here, museum, and go to a typical office building. Now here in Germany, it's a 4-story. It has again efficient insulation, because when the tap system, you want to use it both for heating and cooling, you need to have a good envelope, because there are some limitations in the capacity. So the system was a thermoactive building system with a ground coupled heating and cooling. ventilation with heat recovery, also daylight control of the lighting, and then there was some additional sustainable things like rainwater collection for toilet flushing. So if you look at the building and the concept, you had pipes embedded in the slabs, and you have direct ventilation air with heat recovery. Now, for the heating, you were using a heat pump and a ground source heat exchanger and a heat pump. And you also had a water storage connected to the heat pump, and then it went into the piping into the building. But for the cooling, it was made so you could bypass the heat pump, because basically the water temperature they got up from the ground during summer was about 15-16 degrees, what you would like to use for the supply for the taps system. So you didn't have to use a heat pump. One thing that's, of course, is important if you use a ground source is that you try to keep the ground temperature stable. So you may have to do some simulations over the year. So that's why it's good both to use the system for heating and for cooling, because during summertime when you use it for cooling, you will heat up the ground. But again, then in winter when you use it for heating, you will cool down the ground again. So to use it both for heating and cooling makes it more safe regarding changes of ground temperature, and it makes it also more efficient. As I mentioned, they did a lot to get a lot of daylight into the building, and the artificial light was controlled according to how much daylight was in there. Here you see a summer measurement. Here you have summer months. It's from middle of July to middle of August. All these temperatures you see here are temperatures in different offices, and they are all in the range, in the comfort range. We normally have 22 to 26 degrees centigrade. And the curve here that goes over 30 degrees is the outside temperature. So this combination of the air system and the tap system was able to keep the temperatures within the comfort range. Now, it's always difficult to compare two different systems because often they are in different buildings, maybe different locations, so it's almost impossible to compare. But there's one study which was done some years ago in India and has been reported also in ASHRAE journal, where they had the same building with a VAV system using air for heating and cooling, and the other they had a radiant cooled system. It was in Hyderabad in India. And they took then over heating and cooling period, they took measurements of the indoor environment, but also on the energy use. If you looked at the two, the facades was more or less the same, but what you see here is on the left-hand side, you have the slab system. So you have really a higher building room height because you don't have any suspended ceiling for the ventilation system, because you only need the ventilation you need for air quality, not for heating and cooling. Whereas in the VAV system, you have a suspended ceiling, so you have a lower ceiling height. This, of course, if you have used the same ceiling height also for the taps building, you could have, for example, in a 7-story building, you would save 1 story of materials. So you would save material. So either you can have the advantage of have higher ceilings, or you will use less building material for the same number of stories. If we now look at the measurements of the energy for the conventional VAV, they were using about 40 kilowatt hours per square meter per year, which was pretty good also in India for energy. And for the radiant system, they were using 15 kilowatt hours per square meter per year less. So again, a saving about 35%. And there was no, there were no different in comfort. Even the red, you cannot see it probably. The red dots are measurement for the radiant building. The black dots, are some black here on the right-hand side. Here is a PMV value of 0. Here you could expect about neutral. So compared to how people felt, you were in fact with the radiant a little on the cool side. So you could have increased the temperature a little and then even have a little lower energy than the measured one. So this shows the, even in a humid climate that, like this part of India, that you can use integrated pipes in the slabs. Here's another building, which I think also got an ASHRAE prize. Again, here from Tokyo, I'm taking that because Tokyo is also warm and humid. So if you do a well design, you can also use it in warm and humid climate. I know I have been in contact with some installers in New Mexico in the US, and they do a lot of system both with floor heating and cooling in residential, because there also you have a dry area and you're using both, need both heating and cooling. But in this building, they also looked at what the peak load would be if you had a normal air system or if you use a radiant system. So here's a cooling load in watts per square meter. And they said we can lower from 120 watts per square meter, which we normally would have, down to 90 watts per square meter. So again, this is about 30% lower peak load. And here you see the cooling for the air system is all taking place during daytime when people are in the space, where the cooling with the radiant system is part of it, up to 30 watts per square meter, is really during nighttime until in the morning, and again here after 9 o'clock in the evening. So these are for measurement in those buildings. I haven't, there are examples also from the US, from different buildings, from museums. Here's one where they also calculated on the price from Cooper Union in New York, where they compared the price by an overhead VAV, laboratory plus fan coils in comparison to a radiant ceiling. And that the first cost was they calculated lower, and they also had savings on the utilities. So this building got a LEED platinum. The total energy cost savings were about 34% below the budget, and the energy use was about 46%. I don't know if it still is like this, but there was some measurement done after the building was in operation. Yeah, here it was just, it should have been shown earlier, sorry. It's from the building in Tokyo, showing how they did a CFD analysis. They had the piping, the slabs was a little special construction. This is all concrete, and they had the piping down, you see it's blue, so you can see where they're cooling. So they did that to get some idea about the surface temperatures and how much heat they could remove. So Why would you use low temperature heating, high temperature cooling? Sometimes people also call it low exit system. It's water based, and it's more economical to move heat by water. You have a much higher heat capacity of water than air. So a small diameter pipe, you can move the same energy than in an air duct. That will decrease electricity consumption for the circulation pump compared to fans. By not moving so much air, you have a lower risk of noise, less risk of draft. As I mentioned, if you had integrated, for example, office building, the pipes in the concrete slabs, you may lower the building height because you don't have a suspended ceiling. You don't need a suspended ceiling for the air because you have a direct outside air system where you don't need 4 to 5 air changes per hour for heating and cooling, but only for air quality. Because of the temperature you use for cooling is relatively high, so only a little lower than the room temperature you want, and for heating it's just a little higher than the room temperature you want, you get a higher efficiency of your energy plant if you're using a heat pump, also type of other resources. The capacity is reduced. You have some limitation due to dew point. So normally you need to design, which you should always do, the building very well. So take care of the latent load. You need air. You have to calculate, can the air take care of the latent load that you need for ventilation, or do you need some more air than just the ventilation? There has been some discussion if you have bare slabs, for example, in the ceiling, what about the acoustic? But there are papers also showing that it doesn't become a problem. There's other surfaces that can absorb some of the acoustic. So in general, there has not been reported acoustic problems. So that will end my walkthrough some of the application of radiant heating and cooling systems. Thank you.
That was great, Bjarne. We appreciate it. And just so I think one of the points in the question is, so we heard all the benefits of utilizing water in lieu of air to transfer heat, how the thermal mass of the building can absorb heat and then release heat, and how we can reduce the ventilation just to minimum loads. So is it, I think is the story that the combination of the radiant heating and cooling along with minimum loads and then doing heat recovery for ventilation and then possibly using air source heat pumps or ground source to provide the additional heating and cooling that is required. Is it a total system design we're talking about that's giving you all that benefit?
Well, what you just explained is really a perfect combination of systems. But it's not so that the system require that you have, for example, a ground source heat pump. There is many ground source heat pump installation in Europe. I wanted to do it here in my house, but I couldn't because I was not allowed to make a borehole because of drinking water, clean water. They were afraid that it would get dirty. So you don't need the ground source heat pump. You can also use the system with just an air to water heat pump or other types of energy supply. You could be district heating and cooling systems. I know they are not so common in the US. They are coming here. District heating, especially, we are now talking about low temperature district heating system, but we're also starting with a district cooling system. So it's not that you need a specific combination of system, but this combination you mentioned really makes it very attractive. I think by using this mass, the advantage will be, and we are talking very much here in Europe about energy flexibility and flexible building. That is, when we have to go down to zero carbon emission buildings, we need to use the energy when it's renewable energy available. And by having some thermal mass in the building you can operate with, you have a bigger chance of keeping a good comfort and at the same time trying to optimize your energy use.
Right. Yeah. And I think, yeah, there isn't a huge prevalence of the radiant heating and cooling in New York, where many of our members and viewers are based. So, but I think the message is that it may be something to consider when speaking to your clients and others, given all these different factors and combinations that can help drive down energy use and ultimately carbon use. Well, I think that's it. I didn't have any other questions. So just a reminder for everybody, when you exit out of here, there should be a survey that pops up. So fill that out, and then we'll send you a certificate to get your PDH. So we appreciate everyone attending today. If you have any questions, email us at ashraenyc@gmail.com or visit us at ashraeny.org. So Bjarne, we really appreciate your time today, and wish you well, and thanks everybody for attending.
Thank you. Goodbye. Have a good day.
Oops.